Hey folks, this is a quick video talking about exam answers, the written parts of the exams. And I just wanted to give you some insight on what works and what doesn't. And so some answers, it's okay to take the minimalist approach and not give any extra information. Like in this example problem, I'm asking the student to provide input on why the alkali metals have such low ionization potentials, and I've given them above this a chart of the data of all the first ionization potentials for all of the elements on the periodic table. But I want them to actually use an argument from electron configurations and energy levels and talk about the stabilization of fully filled subshells. And so this student did exactly that. They show the electron configuration here for the neutral sodium atom and for the sodium cation, and the sodium cation having fully filled subshells, and the noble gas configuration has got a slightly stabilized cation electronic structure, and so this causes the ionization potential to be low for sodium. And so this student rightly wrote the cation of sodium drops in energy, thus the ionization potential is smaller. Now I put at risk A. I mean, they got full credit, but they had the very minimum number of words, and they didn't say any. They didn't make any misstatements. They also didn't really tell me why this would apply to all the alkali metals. They just talked about sodium in particular. So this was probably at risk of getting a B, but I thought they answered the question in the manner that I was looking for, and so it was really the minimalist approach, no extra info, and also at risk of not getting full credit. Okay, this one is the ideal amount of information. They show two examples. They show lithium and lithium cation and sodium cation. They show the electron configurations for both. They make the argument that fully filled valence shells are stable and therefore they drop in energy slightly, and that this makes the the alkali metal easier to ionize. They also compare this to noble gases, so this was extra information. They show that the noble gas configuration is lower than you might expect, and therefore it's more difficult to ionize. And so this is I would say a perfect answer for this question. This is the minimalist approach gone wrong, and so they tried to write as little as possible. They messed up a major error here, and I asked about the alkali metals, and they chose boron, and boron is not an alkali metal, so they totally missed that. But I at least wanted to see, and here they have a filled subshell, and that also is somewhat stable, so this part is somewhat correct, but they really don't explain much about the problem, and they make a critical error in terms of the alkali metals. So they did use electron configurations and energy levels, but they used the wrong system, and so they received just very minimal partial credit. This one, they wrote enough, and actually I was able to see that they had a misconception. They talk, this is a slightly different problem, it's the next one in the exam, looking at the half-filled subshell stability and using energy levels and electron configurations to explain the anomaly in nitrogen and oxygen, where nitrogen is harder than you would expect to ionize, and oxygen is easier than you would expect to ionize. And so the same thing can explain both of these phenomena, that partially or half-filled subshells are stable. So in the nitrogen case, the neutral atom has a half-filled subshell, 2p3, and this is unusually stable, so that creates a larger than expected ionization potential to the nitrogen cation. Whereas in oxygen, it's the cation that has the half-filled subshell, so that energy level is stabilized a little bit, and you see a smaller than expected ionization potential for the oxygen. And so they don't really speak in here anywhere about the cations, and they make a misstatement here. They say subshells with only one electron in it. Well, none of these subshells have only one electron in them, and so this isn't applicable in this case, and they're revealing a misconception. And so they lost three points for that misconception. Maybe could have lost a few more as well, but I would consider this an answer that is worthy of a B. They got most of it correct, but it wasn't quite at that fully understood level that I would expect for an A. Okay, now this is an impressive answer for both of these questions. This would be what I call a textbook level of detail. This student runs the risk of not being able to finish, but if they did have time at the end of the exam, then this is an appropriate level of detail. It's just a lot. They're showing me that they understand this, like I said, to the textbook level. This student could teach this material on these two questions. And so if you want a good answer for these two questions here, then these two answers are fantastic. And so you can read them in detail. And then lastly, I'd like to point out an example of being too verbose. And if you're too verbose, you write too much, then this can cause problems because the chances of you making a misstatement are increased the more you write. And so as I was reading through this answer, I saw a misstatement here that says unpaired electrons with the same spin repel each other, which decreases Coulombic repulsion. So they repel each other, which decreases repulsion. And so that's just a contradictory statement. And so it's not to be too critical, it's just that the more you write, the more likely it is that you're going to write something incorrect. And I'm not going to give credit for the correct statements and ignore the incorrect statements. So the more you write, if you start writing wrong things, you're going to lose points. And you lose credibility as you write too much. And so this student addressed most everything correct. I took off a couple of points for the contradictory statement and mainly to send a message that don't write too much. Write just enough to convince me that you know what you're talking about, but no more. And so then this sort of leads into the overall strategy for written work. You know, the number of words and score are not linearly related. If you're not going to get a higher score the more you write. And so that's simply not true. What is true is more of what they would call in economics a Laffer curve. There's a maximum and then it drops off. So what's going on in the different ranges of this curve? Well, down here the student hasn't written enough to convince me that they know what they're talking about. They haven't completely answered the question, and so they're not going to get full credit. Whereas here it's ideal. The student has demonstrated that they know what they're doing. They've answered the question. They've answered it using the tools that I've asked them to use. Like in the two problems shown in this example, I want them to use energy levels and electron configurations. Here the student is beginning to show some insecurity by shotgunning. They're including extraneous information that I didn't ask for. They're using other tools that weren't necessarily relevant to this situation. And then if they go too far, the student has written so many wrong things that they start to lose credibility and start losing points because I am going to take off for incorrect statements. So this is the written work strategy, and hopefully that'll help you frame your answers and also to prepare so that you mentally prepare to write what you know and no more, no less. So show me what you know and do your best. I'll talk to you later. Bye.